Now we are recording. So for the record, we have a course on mapping traits on evolution done by Víctor, I think, to be giving this course. This will be 1.5 hours, more or less.
More or less, I hope it's 1 hour, 1 hour and a half.
Okay, Víctor, audience is yours.
Thank you. No, it's not changing. So if I change the no. Okay, but if I change the slide, it doesn't change there, right?
You need to do it in or just
I will try this way. So, but then no, yeah, but there are some animations that are going to be lost. So, sí, sí. Ahora mismo así, Mashalí no aparece. No, esto no creo que grabe, o que eu quero que grabe é isto, mudar, mas não está a mudar.
Está a aparecer
O anterior.
Estás a fazer em vista. Vira lá para trás.
Agora.
Exato. E pronto, ok.
E agora, num princípio, se eu mudo. Muda a seguinte?
Sim.
Ok, já está.
Muito bem. Ok.
Agora sí, pues. So, thank you for coming. As you know, I'm Víctor López Rojas. Spanish Paleontology is doing now the PhD in geology. Now I will start with a little bit of theory. I will ask a few things. You can answer. You can be wrong. This is the way we learn. Okay? And then we go to our studio. You will know when we are going to our studio. Okay? What you have, what I share with you is everything. The entire script, everything step by step. Now I'm going to show you the first steps, okay? And some of the examples. But for example, if I show now, or I will explain you 7 types of models of evolution, in theory, I will show you 5, 7, I don't remember the exact number. But in the examples are going to be 2 or 3, the main important ones, okay? And later in your scripts, the ones that I share with you is everything. So everything with all the notes. And if you have any question, you can raise your hand and ask me question. If you go to the scripts later and have questions, you can send me an email whenever you want, okay? So first, a few things before entering into mapping traits of evolution, okay? What is a tree? Your answers. What is a tree? The relationship, I mean, it's a representation of the relationship of organisms. Okay, it's a way. What kind of trees can we find? This is a little bit more tricky. I will show you later. And what is the best tree that we can use? There is an optimal tree. There are more than one tree. What can we use? Okay, first, a phylogenetic tree is a diagram, it's a representation that represents evolutionary relationships among organisms. Okay, so what we told, depending on the branching, it reflects how species have evolved from a common ancestor. So we can say that the species A and B are more related to each other than to species E, but they have a common ancestor. If we go farther in the tree, we find more species and we can find more relationships. Okay? For now, we good? Types of trees. We have the cladogram. It's the most basic one. It just shows relative relationships between species with a common ancestor. The additive tree, now it has more information than the cladogram. It has branch lengths, so it shows parameters such as evolutionary change. If we are mapping traits, we can see where the trait started, where the trait appeared, if it was lost later. And then the ultrametric tree. This tree is an additive tree, but with all branches equidistant from the root. Okay, it can be used for evolutionary time. So this one has time with it. And now I'm asking you, which one of these three is a cladogram? The first, with the second, or the third one? So which is the cladogram? The first one? Here. The cladogram, this, okay? The additive tree, the first one or the second one? Okay, and the ultrametric tree? The? The additive tree is the middle one, and the ultrametric tree is this one. But you were right before, because the ultrametric tree has all branches equidistant from the tree and has time, which is what we have here. Okay, there are also a non-ultrametric tree, which is rooted, but without without equidistant tips, so closer to an additive tree. Okay. Now I have said that they have roots, but what is a root? Okay, in a tree, the root is where it varies to the ground and it starts from there, the tree. Okay, a root in a tree is the first node that we start counting. So from where all the nodes descend. Okay, therefore there are roots. There are trees with root and without root. But the main difference between them is that the rooted tree has a direction. So if we go to the left one, we have the root here and we have a direction. We can go before the root or after the root. So we can go more basal or more derived from that node. And if we go to other node, okay, but in this one, there is no root. Here, for example, the node of the root is between bacteria, archaea, and then from archaea appears eukarya. Here is not exactly the same information. However, they are the same species. They both show relationship between species because they are trees, but because of the root, the information that they give us is different. Okay? So, what is the best tree? It is up to you, up to your work, and wherever you want to show is going to be better. Use an ultrametric tree, a cladogram, a non-ultrametric tree. There are a lot of them. You can mix more or less how you want, and depending on what you want to show, is better one tree or the other. Okay, so now that we know what is a tree, what's part of a tree, we can continue to mapping. No, first, what is a trait? Okay, a trait is a characteristic, a feature of an organism. So an evolutionary trait is a trait that can be passed to the next generation for a better survival and can be passed. Yeah. So according to natural selection, if these traits allow for a better survival, they are going to be persistent and they are going to be passed to next generation. Okay. So for example, here, one trait is 4 legs. Another one is amnion leg, egg, hair, mammary glands, live birth. And with those traits, we can difference. This is very basical. This is a cladogram, very basical, but we can see a direction and an evolutionary direction. Okay, we have no time. We are missing a lot of things, but the basic things. So there is something very important for us today, is that the comparison of these evolutionary traits is not independent from the phylogeny or the distribution of the species. It's related to their relationship. If we are adding characters, the relationship between them can change. Okay, so if you go to, a dinosauria phylogeny from 100 years ago, is not going to be exactly the same as nowadays, because I don't know if it was 4 or 5 years ago, there was, yes, 2017, there was a new paper saying that ornithischians and theropods are closer together than theropods to sauropods. And we have the Ornithostelida and sauropod. Okay, so more characters, more features are going to have can change our traits. So our species are going to influence the phylogeny and vice versa. Okay. So to apply the phylogenetic data to our observations, we are going today to account for the phylogeny, okay, which is simple statistics, but are statistics at the end. But adding another observation, which is the phylogeny, the relationship between our species, our observations. Okay. So what we are going to do, we are going to estimate a pattern of evolution. We are not going to see evolution itself. We are not going back on time. We are not going to create an intermediate species. We are not going to see between branches and say, okay, 3.5 million years ago, how the species look like. What were their traits? No, we are not going to see that. We are going to try and understand what our data tells and try and explain evolutionary history. Okay? So for accounting for phylogeny, we need to understand a few basic things, more basic things, before starting to model. Okay? First, the standard regression is as simple as a model, which a dependent variable relationship, so depends directly from an independent variable, and is represented by a straight line. A phylogenetic regression is going to use the same principle, but with another parameter, the relationship between our species. So the assumptions that we can do in a standard regression, we can do also in phylogenetic regression. So if we stand the basic statistics, we can also use for phylogenetic statistics. Phylogenetic statistics, okay? I've just invented that. So we are going to work with species, organisms. They can be alive, they can be extinct, but both of them are tip species. Why are they tip species? Because they appear at the tip of our tree. So if this is a phytosaur tree, so all of them are extinct. But imagine that we expand this until nowadays crocodiles. Most of them are going to be extinct, okay? But we have the relatives of nowadays crocodiles. So we have both of them. But remember this, they are tip species. They are not in between species. They are the final stage of the evolution of each one. So after them, there is nothing more. Even we have crocodiles today, these are phytosaurs, these are totally different. They had their evolution. And crocodiles had another 200 million years of evolution. Okay, but all of them are tip species. They are the final stage. Okay, we are not going to see the middle stage of a whatever. However, what we are going to work, so we have the data from our tip species, but what we are going to infer are the known level. Okay, so the common ancestor from each of a species or group of species. So our analysis are going to use phylogenetic and statistic data combined. So for that, we need hierarchy between them. They are not totally independent. Okay, so if we miss something of both of them, if we miss the phylogenetic data, we are doing just statistics. If we miss the statistics, we are doing systematics. Okay? So there are two ways to account phylogeny, to introduce the phylogenetic information into the statistics. One of them is independent contrast. Information from our observation is independent from phylogenetic relationship. So it's independent from the phylogeny. This is not the best one to use because we are separating statistics from phylogeny. but trying to get them together. An example will be, we have 5 species. So node A will be an average between species A, species 1, and species 2. Node B will be between species 3 and species 4. But node C will be an average between node B that we calculate and species 5. And node D, the ancestor, the oldest ancestor between all of them, will be an average between A and C, sorry. So they are not all raw data. They are going to be estimations, okay, estimations from our raw data. Okay, and the better one, the one that better models and more complex models use are weight observations. So the data that we observe for relative phylogenetic relatedness, it has regression coefficients and are used with matrix algebra, variance and covariance matrix. Now we're starting with a little bit more complex statistics, and I will explain to you. Okay, as the phylogenetic regression procedure. No, it's statistics. We haven't seen any species at all, right? Welcome to nowadays paleontology. So the phylogenetic linear model is going to be simple statistics, but with phylogeny. If the standard regression, the phylogenetic regression, is going to be the same as standard regression, we are going to use the same formula. So a dependent variable, which is dependent from an slope, dependent variable, and an intercept. So we are going to have our species. We can make regression lines between 2 groups and see if there is a significant difference between them, if they are big enough to be studied, if we need more information, less information, okay? But what is the main thing that is going to influence our data? Okay, the sample size is the most important thing that is going to influence our data. A small sample size, usually less than 20 or 30 species or 30 observations, so 20 or 30 species, could give us error of false positive or false negative. Okay. So, for example, it is not the same to do a medical experiment between 30 people than 3,000 people than 3 million people. If from 30 people you got 10 people that got secondary effects, is 1/3 of the people. If from 3,000 you have 100, it's not close to 1/3. If from 3 million you have 1,000, it's even less. So the sample size is really important. Okay. Now, more statistics. First, we need to understand what we are going to see before entering into models of evolution. Okay. So some of the parameters that we are going to see are variance, which is a measure of dispersion, how far from an observation we go. For example, these two groups have an average of 100, but the red one goes from 60 to 125, 130. But the blue one goes from 0 to more than 230. But the average is the same. So the variance, if we pick from any of them, are going to be different. Okay. So a covariance is going to be dependent, one from the other, similar as a regression line or what have been seen until now. Then the variance covariance matrix is a square matrix giving the covariance between each pair of variables. So, for example, 3 variables, ABC, ABC, so the covariance between A and A, B and A, C and A and B, okay? And we have a matrix. So the phylogenetic variance covariance matrix is going to be exactly the same matrix, but with phylogeny involved. So influence it with phylogeny, okay? So how can it be? How different is this? So the phylogenetic variance matrix, we have a simple 3 species example: chimpanzee, human, and gorilla, which share a common ancestor 8.65 million years ago. So if we compare a gorilla with a gorilla, they share 8.65 million years. If we compare a human and a gorilla, they don't share anything. And a chimpanzee and a gorilla, they don't share anything. How are you saying yes? If they share similarities, if they are close together in a tree, as we can see they are really close, how they cannot share anything? Well, because the question is not how much they share, but how much branch length do they share? So if we go from the node of the common ancestor, a gorilla and a human doesn't share anything. A chimpanzee and a gorilla doesn't share anything. But a human and a chimpanzee shares 2.48 million of years of evolution. If we add more species, we add more time, we are going to find more relatedness. Okay? So this is a way to weight our observation. This is the basis of our models. Okay? We are not going to prepare this. We are going to tell our studio to prepare this. Okay? And we are going to see the results after it. However, the most important things of this matrix are that we cannot control them. We are just going to add the data. So we cannot control them. We cannot remove anything from them. And we cannot force them to work as we want. If a gorilla doesn't share millions of years, less than 8 million years with humans, we cannot force them to share that because it's the data, okay? Now, the phylogenetic ANCOVA. ANCOVA, most of these parts, I mean, I am presuming and trying to be the most family friendly that the statistics can be, but next week, Alex is going to explain a few of these parts, or most of the statistics part with better explainings, okay? Now, this is just an introduction to the mapping. But if we don't understand this, or we don't have an idea of this, then mapping is going to be even worse. Okay? So the phylogenetic ANCOVA is going to use the ANCOVA, which is testing where the allometry, that is going to explain that later, which the allometry between two traits includes a shift on an intercept between species implementing phylogenetic framework. What is this? Allometry, which is one part of the body related with the entire body, how they change, or more or less that. And we are going to compare two groups or one species against the entire group, or however we want, but for the ANCOVA, we need to compare. And we are going to use phylogeny for this. So it will help us check if there is any correlation with the regression line. So those two lines over there. And if there is any shift on intercepts. So the difference of mean, if there is a proper significant change or difference between them, okay? So how can we see this in the phylogenetic ANCOVA? So the difference of the slope, the inclination that we are going to see is going to be similar, not exactly the same, but similar as the covariance. So as those variants that were one against the other and how do they relate. So they are going, you can see it's exactly the same basis as a standard regression. One dependent, that depends of one independent. So depending on how do they change, we can infer faster or slower evolution trait. If they change, if one unit of, by each unit of the dependent change one, we have equally allometric growth. If one changes more than one time the other, is going to be either positive, either negative allometric growth. Okay, and this is going to be our basis to rate of evolution of change. And now we can go to models of evolution. So wherever you thought, again, was really a lot of it. And I found, yeah, it was more or less your thought. So the baseline of the model is species B is in these three species, the species B is closer related to C than to A. That is how we read the trees, okay? However, to get into that, we need to assume some phylogenetic distance between them. Okay, here everything's okay. So if we accept that between different species, that can be captured in each branch length. So because the branches are different, we can find different things. It's not going to be constant. In evolution, in nature, nothing is constant. I remember one thing from one of my evolution classes of the career, that the only thing constant in nature is change. Okay, so if we think that having good lines, all equidistant means that, okay, change is constant, exactly no. But it's an assumption that we need to start doing before adding the change, okay? Adding the variation. So the most simple model of evolution is Brownian motion model. Okay, it's going to assume that all rates are the same across lineages. So the common ancestor at node level, remember that we are always working at node level, of two species will be the mean of these traits. It will be the average of those. So there is so in that way, there is equal change between branches. So from that node to the two species, there is equal change on both. Okay. If you remember from a few minutes ago, that are the same assumptions as independent constant. So remember, the node A is going to be average between 1 and 2, node B between 3 and 5, and that. So at the end, there is not the original raw data. It's going to be our statistics, okay? So how do it works? Brownian motion is going to test the rate of evolution in the entire tree. So we cannot say, okay, we are going to calculate for, I don't know, whales, only whales. No, it needs to calculate everything. As just seen, all rates are the same across lineages. Okay, so what it's going to do is do a random walk. It's not the best thing, I know. Something that is random is not good, but okay, it's going to take a random walk. So it's going to be taking values from a normal distribution across the time that we say 1,000 years, 1,000 years, 2,000 years, 1 million years, 100 million years, 500 million years, 1,000 million years, whichever time we say, and then we are going to get another normal distribution, but of a species. However, what we are going to do is the other way around. We are going to test, to estimate, okay? Because our data is this one, is observed trait values. So this branch over here that are all species is going to be the same as here. And then from here, we are going to get the rate of evolution, the rate of change. Okay, so we are going and instead of doing the model prediction, so instead of getting rate of evolution and getting species, we are going to do the other way around. We are going to estimate because we already have the result. We are going to work with the result, which are the type species, which are the species that we have now or the fossil. So the more change in time, the higher rate of evolution we are going to find. It's not going to be the same in 1,000 years than in 100 millions of years. If we compare the rate of change between, I don't know, humans and chimpanzee in 1 million years, It's not going to be the same if we go even farther and we get more species, okay? So it is going to work with the accumulation of variance over time. So our rate of evolution is going to be sigma squared. It's going to be around 0, okay? If we see here, you can see that even this entire range, everything goes around 0, okay? The mean of everything is going to be 0. You can see here also 0, and you can see also here 0. And then there are a few variations of Brownian motion. The lambda model, which rescale the branches based on this similarity between the species. Delta model is going to rescale and show us early against late evolution. Kappa model is for very speciation species, so is going to rescale the branch to see how much a species change, and multiple rates per time. It's going to test for where we think evolution works. Okay. Then we have Ornstein-Uhlenbeck model of evolution, or OU modeling. Is easier to say. This is the most powerful one, but as is the most powerful, is also the most complex. Okay, it is going to assume an optimal value near the root and measures the accumulation of variance. So the same thing that Brownian motion is going to use as rate of evolution, that occurs restrained by that optimal. So the optimal can be or not 0. Okay, it is a multi-peak model, but for making family friendly and easier for us, we are going to use just one peak. Okay? So OU modeling assumptions are similar than Brownian motion model, as we are going to get an optimal value that can be 0 or not. And it needs to be an ultrametric tree to work. So remember, out of the tree with equidistant branch length. So what is the formula of OU modeling? It's going to be exactly the same as Brownian motion, as we can see here, but with 2 extra parameters. Theta value, which is the optimal, that can be 0 or not, okay? And alpha, that is the strength of selection. So how fast is going to that optimal? If we have a higher alpha, it can reach the optimal faster than a lower alpha. However, if alpha is 0, then we go into Brownian motion because we are multiplying by 0 the new parameter that OU modeling is introducing. Okay. So ancestral estimation, Darío, ¿me falta media hora o tengo media? Ah, llevo media hora, vale, menos mal. So ancestral estimation, it will estimate ancestral characters, okay? This is a point estimation. This is how good is our fitting, or how good fits one model of evolution. Remember, until now, we are testing. And this is hypothesis testing. We are estimating, we are that, but nothing more. We are not creating anything new. Okay, we are just testing. Now, the rate of evolution between different lineages. Our basic assumption is the more variation we have, the more opportunity for selection. Okay? It's not selection, it's opportunity for selection. If you have 20 types of wherever food you love, you have 20 ways of, you have 20 opportunities of selection, but you are only going to select one if you have the opportunity to select one. If somebody gives you, okay, you can select 5. You can select 5. Maybe you are going to select 2 because the other you don't like. Then we have that. We have the opportunity for selection. The more variation, the more opportunity. Okay, it does not mean that selection is going to happen. So remember, Brownian motion does not change the mean. It goes always towards 0. However, as we have variation, we have opportunity of selection. So we have rates of evolution. In OU modeling, we can have some change of the mean, so a new optimal, and even a strength. So the selection is also influenced that by those new parameters. Okay. Now, estimating and fitting. I have been saying those words a few times, right? So estimating a model can be done with ancestral estimation or OU modeling. It's going to estimate parameters from our observed data. So from our species, it's going to get parameters following the model of evolution that we chose. However, fitting models of evolution is first fitting a priori. So, okay, I'm going to check this model of evolution and compare with other models of evolution. And then I am going to choose the best fitted one. Okay, the main problem is overfitting a model. Okay, because of what? Small sample size. If we have small sample size, we can have small positives, which will be overfitting a model. The two main, the important thing appear now. So the two main parameters that we are going to work with are the archaic information criterion, IC, that it will check for overfitness. And in case of small sample size, IC with a small c. And sigma squared value, which is our rate of evolution, variation through time. With the amount of variance of the distribution of time. So for fitting, the first thing, for fitting is not the biggest value, it's the lowest value. Why? Because it needs the less for changing. Okay, it's like the Occam rule that the easiest and most simple way to explain anything is usually the best one to explain it. Okay. So for here, it's the same. And when you are, I don't know if you are starting to work with TNT and phylogeny, but however, for TNT and phylogeny, the tree that use less steps are going to be better. Okay? That's why I'm saying in TNT. That's why I say TNT, because it's the one that I work with. Okay? This is going to work with every model, the lowest, the best. So we can compare all of them. Okay, it's not going to be like, oh no, if this goes from 0 to 5, is the same as if this goes from 10 to 15. No, we are going to compare everything. We are going to put the same parameters, the same values, the same assumptions, everything the same, so we can compare them. So the lowest, the best. Then two analysis that we are going to run to see which model works better after getting the best fitted. Bootstrap, that it is statistics, that resamples a single data set to create many simulated samples. So this process allows for the calculation of standard errors, confidence intervals, and hypothesis testing, and the convergence. It is when two distant related species converge or goes towards a same main trait value. So if we can see convergence in species, we can also see convergence in statistics and in our values. So for example, I don't know, two species that looks like a lot, but they are not close related. Any example? You have been seeing one here with one skull and the other that have two holes. The wolf and the thylacine. Generally, if you take the skull, are completely or exactly the same. Exactly, you understand. So they are really close in shape, but they are not the same. There is a convergence evolution. Okay. And now we can go to our studio. Uh, Miguel, vamos a ver si ali está compartida. ¿Está a verse? Está, ¿no? Oh. So, what I will have here are 102, 103, 105, and 104. But a little bit more simple. So if you don't find the same things, it's okay. Okay. So file, if you have done your homework, open file. 102. So first thing first, we need to run the first chunk, which are the packages that we are going to use. So we just go to the green play over here, run current chunk. And if you have installed everything, it will take a little bit of time first time. If you have installed everything, it will run and no error. However, as you can see, there are warning in red and that. It's not the same a warning than an error, okay? A warning is just, okay, check out. Warning, package. The filo was built under this version, or I need to open another package, okay? But it's not an error. You are just, it's just telling you, I have opened this, or you need to upgrade this. But for now, everything is okay. Yeah. So all the information is, so if you, even if you create the new project that I told you to create, you need to copy paste everything there, okay? Because if not, for example, the functions of R that I share here are not going to run because it's not in the project and in the folder that you created, okay? First of all, we need to read our data. So load the data and also load the trees. Yeah, you can, if you want. So you need to load the data and load the tree because we are accounting for phylogeny. So we need to put the tree and the data together, okay? Okay, so everything was read. And now we can, for example, see the tree. Why is not here? As you can see, you see, there are a lot of species that we are going to work with, right? So, and we cannot see them. So I mean, even if we have our data, every single species, we cannot see them. So how can we plot it? So how can we print it in a way that it's easy to see? Well, first of all, we need to align data and tree because there are species that we have not data. Okay. And then, oh, nice, easier. So we only have this species data. It's better than having 300 species, right? With only, I don't know, 60 species data. Then there is this one that is find common ancestor node that it's node 34. Yeah, but I mean, I cannot use easily. I want to see that. So what can we do? This one over here that is save as a PDF. Okay, so PDF in workspace. I name it 102, the first one, plot 3 primates. And here is the coding between the PDF and the dev of is the coding that I'm going to save as a PDF. So I'm telling him to print the tree, so everything with the labels. And also I want to zoom in these two regions from 130 to, and also from 174 to 198. Okay, so if I run it, null device 1, which means, okay, it works and it saved one file. So where do you suppose it's saved? In workspace, because I told him to save it. So I can go to workspace. This first one, it works. So do you remember that big tree that we saw at the beginning? So here it is. Okay, these are all, if I remember properly, they are all mammals. And we can, so I say, okay, so give me the number of each one. So I can look for them later. And I say before, okay, also give me a tree between the species 31 and 90 and 178 to 190, wherever, and zoom them. Okay, so, yeah. Mas num princípio não há problema. Se tenho a mostrar, é simplesmente uma share. So, what can I show you with this? You can have large trees that you can save to see it later. You can zoom them, and even if you say, okay, I want to save two things, if you put it between the PDF line and the dev of, it's going to save each one as a page. So I can have an entire book of scripts, of trees, or wherever I want to save, okay? Ahora se está mostrando, ¿no, Miguel? ¿Puedo hacer así? Sí. Okay, now that we have like the basic of, we can go to the first thing of all, which is standard regression. First, again, we are going to load the tree. Okay, as you can see here, there are a lot of red things, but it's just telling me that the following tips were not found in data and were dropped by the phylogeny. So these species over here, we have no data. So they were took out of the phylogeny. So with what are we going to work? With all of this. So the tree that I showed you before in the PDF. Now, no, we are going to make it easier. We are going to work just with apes. Okay, so it took out all this data, and we are just working with apes. Which is this one. Right? It's going to be easier.
And the open word first. You like can you go to the folder where everything is from? So the one with. I think have to go in the. Right. When you say that you're looking like otherwise everything works. Okay, so they need to be at the same level inside. To not break in. Going to take everything that the one, the one, two, everything you create, because if you look for the cat, it's going to look from that there, it's the right color. I know why. Right, okay. Yeah. Right. The thing is, I did this one to time because around only let's say the fact that that's why. Okay, that's why. Sí, No, pues, si quisiera después guardar todo esto, guardo. Okay, voy como crear una carpeta donde trabajar.
It's like if you don't create a project, it's like, okay, I need to write something, but I don't have I don't know, a paper to write, or my battery ran out, but I want to work with the computer. Okay. Okay, then we are going to do in other way. Okay, as it is, I mean, as you can see here in the script that I have, and you also have, everything is written. Okay, so save as a PDF. You need to indicate the folder and how it is done. Everything is done step by step. So I need to continue. If you want to see models of evolution, okay, I need to continue with the class. If you need anything more, everything is written there. You need to read the README 1 and README 2. Any more problems that this doesn't open and whatever, I'm going to be here usually Thursdays and Fridays, so we can work with that, or send me an email. But I need to continue, or if not, we are not going to see. Okay. Me falta media hora también me puede decir. So, okay, we plot the tree. These are the species that we are going to work with. We are going to create a linear regression. So, a dependent value, an independent value, and a line that relates both of them. Okay, this is the formula. So, the data of the brain, which is my dependent value, depending on the data of the body, which is independent. And these are, each point is one of the species and the regression line between them. Okay. Now, if we want to do the phylogenetic one, we need to do the phylogenetic independent contrast. Okay, so do you remember more or less the phylogenetic independent contrast? That is going to take the data from our observations more or less independently from the phylogeny and get the average and get everything without accounting for phylogeny. So it's a phylogeny without accounting for phylogeny. It's a bit weird, but it works, trust me. So first of all, we are going to get the data. So our new data is going to be this. Can be negative, can be positive, okay? But this is our data, our new data. And we can see them, as I said you, is not going to be the data of the species, but the node level of the species, okay? So the independent contrast of the brain and independent contrast of the body. And now, we can make the regression line of them. As you can see, the points are different, not because of size, but the position, and the regression line is not exactly the same as before. Okay, we have introduced the phylogenetic information and the regression line changed. Why? Because we entered a new parameter. So now we are going to make the, do you remember that variance covariance matrix, the phylogenetic matrix? Okay, so I didn't invent the data. I took it from here. Okay, so I got the 3 species and I got the phylogenetic matrix. So gorilla against gorilla, Homo against Homo, and I don't know why it's not showing like a 3-4-3. So as you can see, I'm having also problems with RStudio. Okay, so here now, 3 against 3. So these are the same numbers that I showed you before. So it was not a matrix that I created from nothing. It was real data. Okay. So now we can. So now that we have the phylogenetic matrix, we have the real phylogenetic information, we can make the phylogenetic regression line depending on, influenced by the phylogeny. So not independent from the phylogeny as we did before. So this is our raw data. And with phylogeny is this one. As you can see, it's more or less the same as the regression line because we have a small sample size. If we have a bigger sample size, we could check if there is a significant or not difference between statistical standard regression and the phylogenetic regression. Okay, and as you can see, everything that I'm saying is here explained. So you later can come here and read. And if anything is not working or you don't understand, and is not here, then you can email me or wait until Thursday or Friday. I'm here in class with you. So now, phylogenetic ANCOVA, comparing one species against the rest or one group against the others. One question, if you put an interrogation before wherever you need help and run that, it opens here in help a quick description of what it is, how to use it, and what are the parameters and arguments, details, and all the things that you can get from there. So for example, there were some of the definitions that I used or that I wrote that were directly taken from here. So if they were two statistics, it was because of RStudio, not because I wanted to make them difficult to understand. Now what is? So again, we need to load our data that we are going to call brain, the dependent value, and body, the independent value. We are going to prepare them. So dependent and independent, we can name it as whatever we want. But if we say dependent and independent, when we are looking later at them, it's going to be easier that, for example, one calling it a cuello and the other arroz. Okay? It's going to be funnier, yes, but it's going to be difficult later to explain in an article why I called it cuello and arroz. So, our basic study is going to be catarrhines against platyrrhines, which are those two groups of primates. Okay, if you don't know them, as I do not know them, these are the data that I took, we can look for them and say, okay, catarrhines, so the common ancestor between Homo sapiens and Paranopithecus, and platyrrhines, the common ancestor between Calicebus and Olowata. How are you going to do it? Okay, so get me from this tree the common ancestor of these two and name it platyrrhines. Okay, and with catarrhines also. So imagine that you have dinosaurs and you want to separate sauropods from theropods. From your tree, you know that this species and these species are theropods. So you can say to RStudio, okay, give me the common ancestor between Passer communis and Coelophysis, and sauropods between Brachiosaurus and Brachiosaurus. And then RStudio is going to say, so between this and their common ancestor, everything are this group, and between this and this, and the common ancestor, everything is the other group. So I don't need to name 300 species every time that I need to work. So just to show you, these are the species that we are going to work with. Okay, around 45, 50 species. We could either put a dot, put the name, or, as I said, put the number. Which are those numbers? Those numbers are, remember from that big PDF that we created? So these numbers. So, for example, if I want to look for species 20, I just go to the PDF, look for 20, and it's going to say, is this a species? Okay? I've tried to be the most family friendly for this. Then we are going to do the phylogenetic ANCOVA of each one. So catarrhines is going to appear later as green, and platyrrhines is going to be as gray. And why is not? Okay, because I need to plot them, obviously. So I need to charge everything of this. So we have each point. So the species plus the point that they appear with. So if it's green, is catarrhines. So between Homo sapiens and Arenopithecus, this is gray, is the other one. And then the regression line of each group. Now we have the regression lines, we have our data and we need to prepare to compare the data. So what are we? So now we are going to prepare the slopes, parameter and the intercept parameter. This is just creating the data. And now we go to the model of phylogenetic ANCOVA. We need to say, okay, this model, so dependent against independent, the data as this formula and create a matrix. Nothing pops up. Why? Because this is only data. I'm not plotting anything. If I want to show me the data, here it is. Each species with its intercept and the independent value. Okay. And now, for phylogenetic ANCOVA, we need to compare two things. So we are going to get the model that we created, that is the basic one, or raw data. And then we are going to create one that has difference in slopes and holding intercept constant, the other way around, and having both different. So now we created the matrix model. We separate them, we separate the intercept, the slope, and compare them. And now we can do the three different phylogenetic ANCOVA and get the data. The reduced model is the basic model. So it has one slope and one intercept, the one from our raw data. So two parameters. If we added the different slope, we have another parameter. So the full model, the 3-1. Do you remember how much needs to be the number to be significant? Bigger or smaller? Smaller than 0.05. How is this number? Bigger. So if difference in slopes, they are not significantly different. If we go for difference in intercept, neither. And if we say, okay, both of them are different, also no. So this can be a few explanations. We don't have any species, but we have more than 40. So it's not a small sample size. Let's go back to this. Do you see anything weird here? Is any species jumping out or far away from something? Which one? 41. If you go to the PDF that I'm going to be faster, that is Homo sapiens. So what are we going to do now? We are going to compare Homo sapiens against every other. It's exactly the same that we have done right now, but just comparing one species against the other. So we say, okay, human, which is Homo sapiens, and then non-humans, well, everything but Homo sapiens. This is going to show the tree. So if we have done it properly, if I plot it, we can see like everything with one regression line and then humans there. So we choose proper, so we choose humans. Well, we didn't choose any other species. Now we are going to compare the intercepts. Why? Because the slopes, we remember that that formula of y is equal to intercept plus slope cross multiplying by the x. That means that for a slope, for a line, you need at least 2 points. If you have one species, you cannot do a line. So we can only compare the intercepts. So we are going to work with the intercepts, allocate them, create the basic model, the model with the intercept, and get the phylogenetic and co. So the reduced model, which is the original one slope, one intercept, and the full model, so the one that differentiates the intercepts. Now the value is 0, which is bigger or smaller than 0.05. It's smaller, so it's significant. So our first hypothesis, this is not a final result, our first hypothesis will be humans have a significant difference between their brain and body than the rest of the apes. Okay, so this is hypothesis testing. So if more than hypothesis testing, creating an hypothesis. Okay? We cannot just finish here, but we finish with the first one, which is 102. I'm going to clean everything here because it's here. Now we're going to 103. Again, we read the packages. And now we're going to the first model of evolution, Brownian motion. Brownian motion works like this. As I say, it's a random walk. So if I keep doing this, it's going to be random, but I am giving a time and a coordinate, okay? So if I say, okay, replicate 100 times or 100 times, and that, we're going to have this. But as it's a random walk, if I keep doing it, but as you can see, all of them goes towards 0. The average continuous mean should be 0. If you do it in your computers, like if right now we do it every time, everyone at the same time, each of us is going to have a different one. Why? Because I say, okay, be random. Okay, so it's going to be almost impossible. It's impossible to do it. However, Brownian motion, if we have a high rate of evolution, more variants. If we have a slower rate or medium rate, as I say here, it's going to be thinner, and a low rate, even thinner. But if we compare the three of them, say before, they no. What is filming? We're going to do like it, that doesn't, like that didn't got film or anything. So for easy sample, we're going to work with just 20 random species with their relationships wherever it is. So it, again, if I do it now and you do it now, your relationships are going to be different than mine. However, that doesn't cares us, because I just want to show you how lambda scales. Okay, because so if lambda is 1, it's going to be the same as our original tree. But if I rescale it closer to 0, branch lengths are going to be closer to the root until they collapse in 0 in an entire polytree. You can see delta. Each one of them is going to rescale either for one or the other. Okay, so we have here the four types. We are going to test now again with the primates. Which one fits better, Brownian motion, lambda, or wherever? Okay, so first I'm going to say, okay, for Brownian motion, I want to fit as Brownian motion. For lambda, I'm going to fill as the model is going to be lambda. For delta, it's going to be delta. And for kappa, it's going to be kappa. And the values that I want are the archaic for a small sample size, which is going to be our fitness value. Do you remember which value needs to be? Big, small, medium, more than 200, smaller than 0.5. For fitness needs to be you have a few seconds. For fitness, the value of a kite value needs to be big or small. To be small. So we have a 200 and a 201 is better than, I mean, that's a high value. It's better than comparing 100 to 102. Yeah, the value itself, so if it's 200 or 100, it's only important if we compare with the other, okay? If I'm comparing 200 with 201, 200 is going to be better fitted because it's smaller. If I'm comparing 100 with 200, it's going to be even better fitted the 100 than the 200. So here I put it nicely, Brownian motion. Fitness, 219. Lambda, 221. Delta, 218. Kappa, 221. Which is the best fitted one? Brownian, Lambda, Delta, or Kappa? What I just asked that. The smallest one. So, which is Delta, followed by Brownian motion, right? So this es el problema de internet normal. También, sí, eso también, entonces ya no hay problema. So, the thing is that Brownian motion is the basis for the other three. Okay, so lambda and kappa are penalized because they have an extra parameter or they are rescaling other way than Brownian motion. And we have 20 species, so it's a small sample size. That's why all of them, even delta, that is better fitted than Brownian motion, all of them are closer one to the other. Okay, so even 218 is better fitted than 219 and 221. They are not really significant difference between them, okay? Now the OU modeling. Really simple. So we are going to say, okay, the distance of the root of the tree, I want to be ultrametric. And it's creating, as you can see now, everyone has the same distance, the same branch length. Okay, not the same distance, but the same branch length, which is different. Now we are going to add, okay, is now ultrametric? Yes. So we can work with it. It's going to sample or for you modeling, if it's 0, so the closest to 0 is going to rescale everything closer to the original tree, but branch lengths are the same. If we go towards 1, it's going to collapse. And now we are going to compare, now that we have a ultrametric tree, Brownian motion can work with ultrametric trees, lambda also, delta also. So all of them can work with or without ultrametrics, but OU modeling needs to be ultrametric. So now we can again compare all of them and see if there is any change. If OU modeling is better, or if we continue having Brownian motion and delta, again, having a better fitness. So you have the spoiler there. Don't tell me that my internet isn't stable. So, Brownian motion, lambda, delta, kappa, OU model. Now again, delta and Brownian motion have better fitness. Again, we are working only with a few species, not all of the trees. So the sample size is really low. That can be influencing this. So now we are going to use lambda, which is the simplest one. Is going to check this similarity between species. So it's the simplest one comparing with the other, because delta is going to rescale because of early or late evolution. Kappa is for really speciation events, and the other one is to check. And OU modeling is really complex. So we are going to work with lambda right now. So we are going to work with lambda and use the PGLS of before. So the phylogenetic regression line and the ANCOVA. Okay, so as you can see, we prepare the data, we get the names of the data, we do the phylogenetic ANCOVA, and create for lambda, and get the sigma value, so or rate of evolution, that is the variance that is going to be the variance covariance. And we are going to save it as a PDF. To make it easier, I already saved it as a PDF. Not here. So the blue line is Brownian motion, and the green line is lambda. All these species are the same as before. So the 41 is Homo sapiens, and the other ones. You can see there is no real difference, no real significant difference, because lambda needs to work at least with between 30 and 50 species. And also lambda is really close to the basis of Brownian motion. That's why we don't see any difference there, okay? But this is how rescaling with, so this is the original PGLS rescaling with Brownian motion and rescaling with lambda. Not real difference, but we are rescaling to another model, okay? Internet went off like 3 or 4 times, but it keeps filming, so we hope okay. So now we are going to do the phylogenetic ANCOVA with lambda model. So we are going to compare the two groups, rescaling to lambda, rescaling to the dissimilarity of species. And again, so remember, this one with the humans significantly influencing this regression line. So the reduced model, the one with no changes, and the full model rescale to lambda with a difference in slope continues without any significance. With rescaling of the intercept, nothing, and rescaling to lambda and changes in both of them, nothing. But as we have said before, humans are influencing this one significantly, okay? However, we have been rescaling this to a model of evolution, depending on the dissimilarity of species. Here again, for helping you remember what is ancestral states. All right. So it's going to estimate ancestral characters states. So it's a point of testing, creating hypotheses of what we think happened depending on what model of evolution we chose. So we prep. No. So we prep the data and do the ancestral estimation. Warning, these data are not in phylogeny, so we kick them out. Doesn't matter. Volto? Ah, sim, mas não. Também isso é mais para mostrar a vocês, isso depois está guardado, ou seja, aparece no PDF guardado, então pode ser ver depois. So these are our species, and we calculate the ancestral state. So the mean value of each one in node at node level. So yeah, it's difficult to see. We can save it as a PDF, but we can also do it like this. So each of these is the ancestral estimation of the node level. So the common ancestor of the relatedness of each species, and we are going to work with that. And these are each one of the values. Okay, it's easier now because we just say the program. These are the values. You get them and you use them. Just give me the results. Okay, so we are not going to work with them. We are just going to work here. So how, I mean, as you can see, that tree was not the best one to see ancestral estimation, to see changes between them, as the numbers were small, the nodes are like, I need to go one by one comparing them. So it's going to take a little bit of time, as always. We can plot them as phenograms with different color of branches, or phenograms with subtrees. This is charging, but for example, for colors, smaller sample, smaller brain size against bigger brain size. We say, okay, this range of colors. So we can say, okay, here have a smaller brain size against the body, against here, which are the Homo sapiens. Okay, and in the other ones are going to show it other way. Okay, I promise this didn't take so long last time that I checked it. I don't know if it's internet or a studio or what, both of them. Okay, so this is the phenogram without colors because I didn't give it to change colors. Okay. And then we could use ancestral estimation to rate our models of evolution. So I am studying 103. I need to do yet 104 and 105. As you can see, 1 hour and a half has passed. About a lot of statistics, a lot of things, a lot of connection errors. However, you have all the material. You can just run the chunk, see what it means, look for it, and later ask me. Okay? I have written this or copy pasting and making it the most family friendly possible, so it can be seen not that this but charge it happens only once every 10 times. That is charging everything before giving me the result. But usually with this sort of coding, so you code everything, you say, okay, give me everything, take every parameter, and then give me nice, with this coding is give me easily and nice, so I can read it and use it. Okay, so this is every parameter, everything. And with this, I say, okay, give me in an easy way that I can run it, that I can see it and I can use it. So which is the best fitted now? Delta again. It will be ancestral estimation with different rates. So Brownian motion and the I don't remember the name of this one, and because it was really big one. The multiple bias Brownian motion, so it's going to estimate more than one variable, not one bias, but a lot of them. But because I remember that this took a lot of time. Okay, so this is I'm going to buy a Wi-Fi only for this. So this is the entire Brownian motion, basic Brownian motion, and this is multiple variants of Brownian motion. They look almost the same, but if we go, for example, to this group over here, this node between these two species here is closer, I mean, is farther in time than in this moment. If we go to this between Homo sapiens and the pans, here the value near the root is different than here. Okay, so depending on which one, we are going to get different values. How we choose the best one? With the comparison that I have just shown you with which one is the fittest one. So the fittest one is the one that we are going to plot, the one that we are going to get the information, and the one that we are going to use. Okay, there are still another two scripts that I would like to show you and make it as easy and as nice to explain. But then Dario will not have time for his one. And we need to make a little break because there was a lot of information, a lot of missing information that didn't charge. So thank you very much. Sorry for the problems. If you have any problem again, you can mail me or wait till next week and show me in your computer. It's going to be easier. If not, send me an email with the print of this happened. Okay? And let's have a 10 minutes break. This.
Yeah.